In section 4.5, you're going to be learning about logarithmic properties, and these seem very random when you first learn them. So if I am taking two things and I'm multiplying them together and taking the log of them, remember that your answers to these are exponents. So if I'm multiplying bases, I would add the exponents. In the second one, if you are dividing these two things, remember that when you are dividing bases, that you subtract their exponents. And then the last one is actually going to be one that you're going to use quite a bit. So if you have this exponent that is out here, then it will come to the front if you are taking the logarithm of that expression. So we're going to be doing several examples of this, and we're going to take these one at a time. You will need to practice these. Even if you finish the homework, you want to go back and look at it, because we don't have another test until the end of chapter 9. So we tend to forget this chapter because we'll go into chapter 9. So be sure that you practice these and make sure that you completely understand them. So for this first one, we're going to use that we have an exponent up at the top, and the way I always have drawn this is to just do this, and that way you know it comes out front. So I have 3 log base 8 of 8, and I know that log base 8 of 8 is going to be the number 1. So this answer is 3. All right, the next one, instead of having all numbers, we have an expression. So I'm seeing that I have these two logs are added, which means when I look at these two things, I'm going to multiply them. So this gives me log base 3 of b times b plus 5, which is b squared plus 5b. Now, thinking about this in the opposite direction, you're always going to want to factor completely when you go the other direction. All right, so this next one, we have log base 4 of 5. I'm going to leave alone for right now. And now I'm looking at the fact that I have this number up at the top, so it's going to go up and become an exponent. So I have log base 4 of c cubed. And then I'm looking at the fact that I'm adding these. So that means that when I look at this and this, I'm going to multiply those together. So I have log base 4 of 5 times c cubed. So this is collapsing your expressions. So practice a few of those. Make sure that you're understanding that when you go from one direction to the other, that your logs decrease in size. If you're collapsing, they'll increase when we expand. All right, this next one, I have a 2 out front, and I'm going to draw it like this because it goes up as an exponent. So this is log of 5 squared, and then I'm going to just write log of x. Notice for me that there is no base that's written, so these are a base of 10. I know what 5 squared is, so I'm going to replace that with the number 25 because that's what that is equivalent to. And then I'm noticing that I am going to subtract. So this subtraction means that as I look at this number and this variable, you're going to be dividing those. So this is the log of 25 divided by x, and that would be your final answer. So those have all been collapsing them down so that you only end up with one logarithm. So in this next one, I'm going to be expanding. So the first thing I'm noticing is that this is division. So if I have division, I'm going to take the log of my numerator and I'm going to subtract the log of my denominator. Now, if you have a log that's written, make sure that you don't lose it. You will have to maintain that. And if not, we know that it's a log of 10, or if it's natural log, it's a base of e. Now, this is where most students think they're finished with this question. However, this is 9 times b. So this is going to be the log of 9 plus the log of b. And then I'm going to subtract the log of 11. So that is fully expanded. This next one looks very similar. Notice, please, that you are dividing here. So you have the log of the numerator, which is x to the 14th, y to the 14th. And then I'm dividing, so I subtract, and then I will have the log of z to the 8th. Then I have these two things are being multiplied, so that will expand and become log of x to the 14th plus log of y to the 14th, and then I subtract log of z to the 8th. Now again, kids like to stop here and think that they're finished. However, each of these exponents has to come out to the front of their individual terms before we can say that we're finished. So this is 14 log of x plus 14 log of y minus 8 log of z. There's a change of base formula that comes up sometimes. So if the base that you're given down here is not a base of 10 or e, then your calculator is basically rendered useless. So what this change of base formula does is give you a way to use your calculator in order to find these, even if the base is not one that we're used to working with. So if we look at this first example, I have log base 18 of 26. Well, 18 is not a base that will result in 26. So using this change of base formula, I do log of the number 26, and I divide it by the log of the number of the base, which is 18. So on your calculator, you're going to hit log of 26, and this is going to give you this big decimal of 1.414, and I'm just going to put ... It's longer. All right, and then we do the log of 18, and that's going to give me 1.255 ... All right, keeps going. So if we divide those together, now a lot of times kids will want to type this in at the same time, which you can do, but you have to make sure your parentheses are good. So you have to put this in parentheses, then hit the divide key and put these in parentheses. So you have to be careful, because if you don't put the parentheses everywhere they have to go, then your calculator makes the mistake because you haven't told it exactly what you want. So for this one, I get 1.12722 and ... It keeps going. All right, just to practice again, we have log base 4 of 20. Well, there's not an exponent that I can raise 4 to that I know of right off the top of my head that will result in a 20. So we use the change of base formula. We have log of 20, and I'm going to divide that by the log of 4. Again, typing this in very carefully with parentheses, we would have log of 20, and then divide that by the log of 4. And we get a final answer of 2.16096 ... because it is longer. So if it doesn't tell you where to round, make sure you give it the entire decimal. If it does tell you where to round, be very careful to do so appropriately. So for the next few questions, it is telling you to solve. So we're going to be using the properties, and then we finish the question. So the first thing I'm going to do is rewrite this, because this exponent goes up to the top. So this is going to be the log base b of 8 to the 1/3 power. But I can abbreviate or simplify the cube root of 8, because that's what that's equivalent to. All right, this is the cube root of 8, which is the number 2. And that would be your final answer for that question. All right, next one, I have a -1 out here. And if I put that up to an exponent on the 1/2, I'm going to have log base b of 1/2 to the -1st power. Well, if I take a fraction and raise it to the -1st power, it becomes a whole number. So this is log base b of 2 again. All right, next one. Again, I have this exponent out here, so I'm going to bring that up to the top. So this gives me log base b of 4 to the 1/2 power. Well, that's just the square root of 4, which we know is the number 2. So this is log base b of 2 again. Next question, I have a subtraction here, which means I'm going to collapse this down. So I have log base b of 16, and I am dividing that by 8, which gives me log base b of 2 again. And last but not least, we have this plus sign. So that means I take log base b of 1/10, and I'm going to multiply that by the other, which is 20. So I know that 1/10 of 20 is also 2. So log base b of 2. Now, I'm going to collapse this down. This question actually is a multiple choice question on your homework. And what it does is ask you which of the following are equivalent to log base b of 2. So you are seeing 5 different ways that you ended up with the exact same thing. All right, for the next couple, we are going to be expanding these. All right, so I'm going to look at what I've got, and we're going to make this into the longest version of itself, if you will. All right, so we have log base 3 of the first one, which is x to the 4th. And then I am multiplying, so I'm going to add, and I have log base 3 of the radical. So this is the cube root of y to the 11th power. Now, this exponent has to come out front. So this is 4 log base 3 of x. And that term isn't going to do anything else. Okay, that one is finished. Now, what I am going to do is with y to the 11th under the cube root, I'm going to change that into y to the 11/3 power. Y to the 11/3 power. And what that does is put this in a format that I can pull this forward. So this is 11/3, and then I still have log base 3 of y. And that is as expanded as that can be. The next one, we're looking at something that starts out as a fraction, and before I start working on expanding it, I'm going to factor it, okay? So the top is going to factor into x minus 2 and x plus 1 in the numerator. And in the bottom, I have a GCF of x, which gives me x times x plus 1. Now, I know that I can do that because those are twins, and if I am dividing and have twins that are exact factors, then it will leave me with an expression that looks like this. Because this is being divided, that means I'm going to subtract the 2 separate logarithms. So I have log base 5 of x minus 2. And I'm going to subtract from that log base 5 of x. So this next one looks very similar. The only difference is that I have a natural log, but that does not change anything about the exponent rules because the natural log is also a logarithm. So the first thing I'm going to do is separate this so that I'm subtracting. So I have the natural log of x squared times the square root of x minus 1. And then because I'm dividing, I subtract. So I have the natural log of the expression 3x minus 20. Now, as I'm looking at this, I realize that those are being multiplied, so they have to be broken down farther. I have x to the 12th, and I am multiplying those two factors together, so I add, and it's the natural log. And I'm going to rewrite this as x minus 1 to the 1/2 power. And then I'm going to subtract the last term, which is natural log of 3x minus 20. The only thing left to do is take these numbers out to the front of each of these terms. So we will have 12 natural log of x plus 1/2 natural log of x minus 1. And lastly, subtracting the natural log of 3x minus 20. This next question gives children some issues because we forget at the very beginning of this to rewrite this as the factored form, which is y plus 6, y minus 6. Then we have y plus 5 to the 10th power. And then we're going to divide that by y plus 6. And I have to take care of this big radical that we started with here. All right, so that becomes a 1/2 all the way outside. Now, the reason we do this is twofold. We're going to take this and bring it all the way out front, and I'm seeing that those can go away. So I just uncomplicated it just a little bit. So the 1/2 is out front. I have the natural log, and the only things that are left are y minus 6 as a factor and y plus 5 to the 10th as a factor. So now those two things are multiplied together. So I'm going to have 1/2 natural log of y minus 6. And then I'm going to be adding, but here's the mistake also that kids make. This 1/2 is out from every bit of that. So you have to consider that this is going to have to be multiplied back in. So we will have the natural log of y plus 5 to the 10th power. And then this 10 can come out to the front of this term. So I have 1/2 natural log of y minus 6. And then I'm going to have addition of 1/2 natural log of y plus 5, because I have distributed 1/2 and then times 10. This 10 has to come out front with the 1/2 that came from out here. This 1/2 goes here, and it has to go to this term. So I know that this is 1/2 natural log of y minus 6, and then 1/2 of 10 is 5 natural log of y plus 5. And that would be my final answer. For these next questions, we need to talk just for a second about what happens if I take the natural log of e, and what happens if I have e to the natural log of some variable or number. I'm just going to call it x. So if I have the natural log of e, this is a logarithmic expression. So there's a baby base of e here, and I'm going to set this equal to x. So to change this into an exponential, then I'm going to have that baby base of e becomes big base e, and I raise it to the x power, and that's going to be equal to e. So x is equal to 1, because e to the first power gives me 1. Excuse me, e to the first power gives me e. So anytime I've got the natural log of e, I have to memorize the fact that that goes to the number 1. Natural log of e is just the number 1. So anytime I have e to the natural log of x, I'm going to set this equal to some variable, let's call it y. So this is exponential, and I'm making it back into logarithmic. So if I have this big base e, then it becomes baby base e right here that we don't write. All right, the exponent goes to the other side of the equation, and then the y is left to go here. So in this case, y is equal to x, because the bases match, the logarithms match, so then what I'm taking the natural log of has to match. So that means that if I have e to the natural log of some number x, then it's just equal to x. Now, knowing those two things is going to help me, but I am going to expect you to use the rules that we have. So in this case, I have e to the natural log of 4. Well, that's exponential, so I'm going to set it equal to y and solve for y. When I change this big base e becomes this baby base e right here that's not written. The exponent goes to the other side of the equation, so that's natural log of 4. And then y is left to go here. So if I'm solving for y, then y is equal to the number 4. All right, much the same way on the next one. We're going to rewrite this. Natural log, baby base of e. The exponent goes to the other side, so that's the natural log of the square root of 6. And if we set that equal to y, then y goes here. And the only time that's going to work is if y is equal to the square root of 6. So for the next one, we have the natural log of this expression. So I'm going to set that equal to x and solve for x. So again, changing to exponential, I have e, this baby base that's written right here that we don't see, raised to the x is equal to the seventh root of e to the second. So what I have to do on this one is rewrite this radical as a rational exponent. So that's e to the 2 over 7. So then x is equal to the number 2 over 7. Next one, we have set this equal to x and solve. So this baby base e that's here becomes big base e raised to the exponent is equal to 1 over e to the 8th. So I do have like bases, but they are not in the proper location. So this becomes e to the negative 8th. And I know that x is equal to negative 8. And last one of these, we have e to the negative 11 If I set that equal to x, then the baby base e becomes big base E raised to the x exponent. And then this is e to the negative 11th. And I know from that that x would have to be equal to negative 11. Make sure you show the steps in this on your homework. So on these two, I'm starting with the logarithm. So I'm going to set this equal to some variable, and you can call it whatever you want. Just to change it, let's put this equal to r. So I'm going to change this into an exponential expression. So this baby base 6 becomes big base 6. Raise it to the exponent over here of r, and then it would have to be equal to the term that is left. So then r is going to be equal to the number 5. Similarly, you could have rewritten and taken the 5 out front. So this is 5 log base 6 of 6. And I know that the log of base 6 of 6 is 1, so that still gives you the answer of 5. You don't have to do it both ways, just pick one. And this last one, we have set this equal to r again. So rewriting, I have 3 raised to the r exponent is equal to 1 over 27. And I know that I can rewrite 27 as 3 to the negative 3rd power. So r is equal to negative 3.